Okay, so welcome back to this video in which we are taking the convolution of two random variables which are distributed, gamma A lambda and gamma B lambda. And now what we're doing is we're viewing A and B as just being positive real numbers. Okay, so they can be any two real numbers that are greater than 0. And of course lambda also has to be greater than 0, but that was, lambda could be any general positive real number, and this argument would still apply basically. So now the difference is that we're not assuming that these are integral values, okay? So, the first thing to note is that x and y are going to be independent. So we're going to insist that x and y are independent. We're taking the convolution of two independent random variables. In this case, in this intuitive case here, where x represented the time at which the A female arrived, and y represented the time after the A female arriving at which the B female arrived, so the amount of time between the A plus B female arriving and the A female arriving, those were obviously independent in this case, because the amount of time between 0 and the A female does not affect how much time you're going to have to wait from the A female onwards to get another B emails, basically. So this interval here is basically completely independent of this interval. So x and y in this intuitive case we were viewing them as being independent. So that's going to be an important assumption. We're going to assume that x and y are independent. So if we want to build a joint probability distribution, basically, so now let's say we've got a more abstract probability space here, and we've got two random variables x and y which are mapping you onto the positive real numbers, and they are going to be gamma distributed, so x and y here, and they're going to be gamma distributed, so it's 0 to infinity. Okay, and remember they can only take on positive values, so x again is going to be gamma distributed with parameters a and lambda, and y is going to be gamma distributed with parameter b lambda. Okay, right, so if we want to make the joint random variable x and y, then because the two of them were assumed to be independent, then that means that we can just take the PDF of this one and multiply it by the PDF of this one, and it's going to be defined on the positive numbers cross the positive numbers. So it's going to be defined on a subset of R2, basically, so like that. So if I draw the R2 plane, both of these random variables were only defined on the positive real numbers, so these were only defined on this bit here. Now this one, as a consequence, is only going to be defined, or in fact it's not going to be defined actually when you have 0, because 0 isn't included in either of these. So it's going to be defined basically on this bit here, this first quadrant of the R2 plane, okay? Alright, and if we want to know what the probability density function of this joint random variable x and y is, as a function of little x and little y, where we'll label this axis little x and this axis the y-axis, okay, that's going to be the product of the marginals, because the marginals are independent. That's just the definition of being independent, that if you know what the value of x is, it tells you absolutely no information about the value of y, basically. So, it couldn't possibly be any other case than this, because if you had any other case than it was just multiplied by this, it would imply that somehow knowing what this value was, knowing what the x value was, told you something about the value of y. Okay, so now let's plug in what the PDFs for the gamma distributions are. So the PDF for the x random variable is going to be 1 over gamma of a, so just this is the PDF of a gamma distribution, so 1 over the gamma function evaluated at a, lambda times x to the power of a, e to the negative lambda of x, and I apologise that it's getting a little swashed down there, divided by x, basically. And then similarly, the PDF for y as a function of little y is going to be, this time our parameter is b, so we put in 1 over gamma of b times lambda y to the power of b, e to the negative lambda y over y. Okay, that's looking good. Right, so if we just multiply those together, we'll get what the joint PDF is equal to. So this is the joint PDF. So remember, every outcome in this abstract probability space is ascribed an x value by this function x and ascribed a y value by this function y. This joint random variable is just describing an ordered pair, and the ordered pair is basically going to be, it's going to ascribe it So if x that maps s onto x of s, then this x comma at y, the joint random variable, is going to map you onto the ordered pair xs, ys, where xs is what x maps s onto, and ys is what y maps s onto. So basically, it's a very simple idea. Okay, and if we want to know the probability density function that you're at any point little x, little y, basically, then this is the way we're going to calculate it. Okay, so multiply those two things together, and we'll get 1 over gamma of A times gamma of B, and this is a big mess, isn't it? Then we'll pull out, in fact, I'll do it in more steps, so I'll just multiply them together now. So we'll get lambda x to the power of A, then we get lambda y to the power of B, over x times y, so getting those two bits and this, and this, and now we have the e to the minus lambda x and the e to the minus lambda y. So I'll combine those together to get e to the minus lambda x plus y. Okay, so it fits on one line. And now what we'll do is we'll pull out those lambdas, basically. We'll have lambda to the a and lambda to the b, and those will combine to make lambda to the power of a plus b. So we'll get 1 over gamma of a times gamma of b, lambda to the power of a plus b, x to the a, y to the b, over x times y, and then we've got e to the negative lambda of x plus y. So there is the joint probability density function. Now what we want to construct is the convolution. Okay, so x plus y, and basically we want to know what is the probability density function that it's going to equal a certain value. So we want to know what we want to know is this value of x plus y. Firstly, what real numbers is it going to map you onto? Think, is it going to map you onto -1? Is there any outcome in here that is going to be ascribed a negative number by x plus y? Well, what is x plus y? It's the x value that s takes on plus the y value that the s is mapped onto. X and y map you onto strictly positive numbers. So when you add them together, you are also going to get a strictly positive number. So x plus y is going to map you onto 0 to infinity. So everywhere else, on all the negative numbers and on 0, the PDF is going to be 0. So that's the first thing to note, that the convolution PDF is going to be 0 on those negative numbers. Now, let's just concern ourselves with what the PDF is going to be at a certain positive number. So let's say what we want to know is what is the PDF of this convolution x plus y as a function of, let's say, little t, where t is some positive number. So that means that we want what we want is to work out the probability using the fact that we know this joint probability density function. We want to know what is the probability density of a certain well, we want to know what's the probability density function of a certain value of t. So if we use, basically, let me draw some pictures. We're running out of paper. Let me draw you a little picture here. So we have 0 here, and t can take on any positive value here. So basically pick one of those t's, and then if we multiply that by some tiny little interval, delta t, then that should give us the probability that you're within that event, that you're within that little interval. Now what we need to figure out is what does that little interval, t to t plus delta t, correspond to in this picture over here. So we need to get the corresponding event back in here, and then we need to work out what's the probability of that event in here by using the fact that we know the joint PDF here. Okay, so what is this event going to be basically? Well, if we take let's try and find the line that x plus y is equal to this constant t. So let's look at what subset of points of the plane are all going to be mapped onto that value t by this function x plus y. Well, that's just going to be where little x plus little y is equal to t. So that's just a straight line, basically. So if we want to draw this straight line on, then basically, then let's say, okay, evaluate this at x is equal to 0, then we get that y is equal to t. So when x is equal to 0, y is going to be equal to t up there. Now, of course, x cannot equal 0 because it's got to be a strictly positive number. But for the purposes of drawing the line, it's going to be useful. So we'll put t up there. Similarly, if we evaluate at y is equal to 0, we get that x is equal to t, so we get some point down here. So basically, we can draw a straight line between there, and that is the point. That is the set of points which are all going to be mapped onto this point t over here. Okay, right. So we could then imagine doing a similar thing for t plus dt, delta t rather, and that will be basically if you would put t plus delta t. Well, basically what we're now going to say is we want the curve to be x plus y is equal to t plus delta t. So I want to work out what subset of points on this plane corresponds to are all going to be mapped onto the value t plus delta t by this convolution formula over here. Okay, so if we put in y is equal to 0, again we'll get that x has to be t plus delta t, so here is t plus delta t down here. Similarly, if you put in x is equal to 0, you'll get y is equal to t plus delta t, so that's up there, t plus delta t. And then if we draw a straight line for that as well, it's going to be something like that. So basically, oh dear, this interval in the plane, hopefully you can see, is going to correspond to that subset there, the bit between those two lines. Okay, and as delta t gets very, very small, it's going to converge on being just a line. So if we want to find what the probability density function, what the probability of this event is, what we basically need to do is integrate over that event, the joint probability density function, basically. And if we make delta t very, very small, what this becomes approximately equal to, just evaluate the integral along the line x plus y is equal to t, and then times it by the width of this interval here, delta t. It becomes approximately equal to that, basically. It converges on being true as delta t gets smaller and smaller and smaller and smaller. Okay, right, so let me get another piece of paper and we'll perform that integral. So, basically, the assertion that I just made is that if delta t is very, very small, then the probability of this interval here, which is this probability density function evaluated at t times delta t, is approximately equal to, and converges on being equal to, the integral along the line. So let's just put the integral of the joint PDF, xy, as a function of little x, little y, and I'll put temporarily just along the line x plus y is equal to t, so we'll sort that integral out in a moment, and then times that by delta t, basically. Okay, so let's try and sort out what this integral is. Well, what we want to do is effectively we want to integrate along the x values from 0 to t, and the y will take on the y value will be determined by the x value. So basically what this is going to become, this integral here, is the integral from 0 to t. So basically we're integrating along the x-axis. So I'm saying, okay, we want to integrate along that line. So each of the points along that line, x plus y is equal to t, has a corresponding point in the interval 0 to t along the x-axis. So we'll use that fact to make this easier, basically. Okay, so we'll then say, okay, stick in the probability density function, so this joint probability density function, evaluated at that value little x. Now, for each value of little x, there is a fixed value of little y, because remember, we want to evaluate the probability density function at that point, little y there, okay? So then what we do is we stick in what the value of y has to be, and we know that that curve is the equation x plus y is equal to little t, which tells us instantly, if you give me an x value, I instantly know what your y value is, because remember, t was a fixed parameter. So now y is equal to t minus x, so we substitute that in. So that basically says, okay, for each of these values from 0 to t, each of these x values from 0 to t, you go up to that x value and you say, okay, the corresponding point in the plane to that x value, because we're integrating, remember, along this line, and I think I should probably draw another picture because that one's getting a bit crowded. Okay, so let me draw another picture here. So here is our line, x plus y is equal to t. Here. So this is a t, this is a t, and we want to integrate along that. So basically, instead, what we're saying is we're going to integrate along this x-axis down here, and we're going to make sure that what we're integrating is the PDF evaluated at the corresponding point here. So for a value x, we need to evaluate the PDF at its corresponding point on the line, basically. And we've chosen to make the corresponding point along the line x plus y is equal to t, the point that's directly above it, because that's a very nice one-to-one correspondence. Every point on the line is going to have a point on the interval 0 to t corresponding to it. Okay, so we evaluate the PDF at its corresponding point by saying, okay, the x value is going to be x, the y value is then going to be t minus x, because the curve is given by x plus y is equal to t. Okay, so then what we need to do is multiply that by dx to turn it into, to an extent, an area. But what you might be thinking is, don't we need to multiply it by well, basically what that's going to do is turn it to an extent into a probability rather than a probability density. So we're integrating that so that it gives us a tiny little probability along delta x, and then to turn it properly into a probability, what you then need to do is multiply it by the delta t to turn it into because the probability density function, the joint probability density function, needs to be multiplied by two changes, basically. It needs to be multiplied by an area rather than by a length. Dx is just the length. Times delta t then turns it into an area. And basically, as delta t is very, very small, this is approximately equal to the probability that you are within that interval. So if I draw here is t, and here is t plus delta t on the positive real number. So this is x plus y, basically, the convolution random variable. And if you want the probability that you're in that interval, it's approximately going to be equal to that. Now, if we can obviously cancel the delta t's, and if delta t is made really, really small, then this becomes approximate, this converges on being true. Okay, so then what we have is this convolution integral to do. So we get that the PDF of x plus y as a function of t is going to be the integral from 0 to t of the joint probability density function, which is something we've already worked out. It is this thing here, basically. So let's stick that in. Are we going to have room there? Let's have a go. 1 over gamma of a, gamma of b, and then we have lambda, turn that into a lambda to the power of a plus b, x to the power of a, y to the power of b, e to the negative lambda x plus y, oh dear, and of course we were meant to evaluate y at t minus x, so I'll do that in a moment. I'm just writing in the PDF, so remember that y needs to be replaced with t minus x. Where were we? Then divide by xy, and then you obviously have the integral dx, okay? Right, so let's turn it into what it actually needs to be for us to integrate it. So we are evaluating y at t minus x. Okay, so this becomes the integral from 0 to t of lambda to the power of a plus b, x to the power of a, y to the power, oh dear, what am I doing? Y we are substituting with t minus x, okay? T minus x to the power of b, okay? Then we get e to the negative lambda, and then we've got x plus t minus x, so that's nice because that's the x's are going to cancel there, dx, and then we've got all over gamma of a and gamma of b are just constants, times x times t minus x. Okay, right, now let's pull out some of these constants. As far as the integral is concerned, lambda to the power of a plus b is just a constant. 1 over gamma of a times gamma of b is just a constant. Are there any more constants? And we can obviously cancel these two x's here, but those are the only constants. So we're going to pull out this great big constant at the front here, that thing, okay? Oh, and this is going to be a constant because, I didn't stress that. So when the x's cancel, because this x minus this x becomes 0, what we end up with is e to the negative lambda t, and that plays no part in this integral. T is just a constant, lambda is a constant parameter as far as the integral is concerned. So let's pull all of those out. I'm going to pull this thing out as well here. Right, okay, so then what we get is we get gamma to the power of a plus b, e to the negative lambda t over gamma of a, gamma of b, and then what we have is the integral from 0 to t of x. Now we'll cancel this this x to the power of a with this x down here. We'll get x to the power of a minus 1 times t minus x to the power of b minus 1 dx. And you should be thinking, oh wow, that looks very like a beta distribution. So let's convert it. Let's do a substitution to turn this into a beta distribution, because at the moment it's not a beta distribution. At the moment you've got this hideous t here, and you've got a t up here. The beta distribution, remember, is defined on 0 to 1, not 0 to t, and it's got a 1 minus x there rather than a t minus x. But it's close. So, and we can turn it into a beta distribution nearly using a substitution. So let's say u is equal to let u equal what are we going to let it equal? X divided by t, I think would be a sensible thing to do. Why have I made it equal that? Because if I define it to be equal to that, what are the limits of this integral going to become? This lower limit, if I put in x is equal to 0 here, I'm going to get that u is equal to 0. That's good. If I put in x is equal to t, I'm going to divide t by t and get 1. So the limits are going to change to be exactly what I want them to be. Okay, right. Now let's convert the differential. So du is going to be dx over t, and dx is therefore going to be equal to t du. So this integral here, let me highlight it with a blue pen. This integral we are going to convert into another integral, and it's going to be converted into the integral from 0 to 1, so we've adapted the limits. Then we substitute in x is equal to t times u, so we put in t times u to the power of a minus 1. We get, from here, we get t minus, and now we substitute in tu for x to the power of b minus 1, and then we substitute in t du for dx here. Okay, right. Now, factorize out the t's basically. So we then pull out the t's from these exponentials here. So we get t to the power of a minus 1 times u to the power of a minus 1 times t to the power of b minus 1 times 1 minus u to the power of b minus 1 times t basically du. Okay, right, as far as this integral is concerned now, the t's play no part in the integral, so pull them all out, and you'll get that this is t to the power of a minus 1 plus b minus 1 plus 1 from this one over here times the integral from 0 to 1 of u to the power of a minus 1, 1 minus u to the power of b minus 1 du. Okay, right, now put back this thing that we had originally over here, which is lambda to the power of a plus b e to the negative lambda t over gamma of a, gamma of b, and alter this thing here. So cancel this minus 1 with this plus 1 here, like so, and then split this back up basically. Split it up into, how am I going to do this? Right, okay, let's just write another line. Firstly, I'm going to split up this lambda to the a so the and plus b into lambda of a, and then I'm going to split up this t a minus 1 plus b into t to the power of a. Then I'm going to have, oh wait, what am I doing here? No, sorry, get rid of that, scratch that. I'm going to split this t here, t to the power of a minus 1 plus b, into t to the power of a plus b over t. And now, so basically that's exactly the same thing. All I've done is say, okay, I don't want that minus 1 there, so I'm going to just have divide by t. So that whole thing there is just equal to t to the power of a plus b divided by t. Now what I'm going to do is combine this t to the power of a plus b with this lambda to the power of a plus b to get that this is lambda t to the power of a plus b. Then we've got e to the negative lambda t over t from here, so we've got the over t over here, and then we've got this mess. We've got this 1 over gamma of a, gamma of b, times the integral from 0 to 1 of u to the power of a minus 1, 1 minus u to the power of b minus 1 du. Okay, right, and we'll call it there for this video. What you should be thinking is that this looks exactly like a gamma distribution. The convolution has to be a probability distribution, and this is, as far as the t is concerned, this is just a constant. There are no t's anywhere in this. This integrates out to become some constant. This is just some constant. This has to be a probability distribution. Therefore, it has to integrate to 1. We know that gamma distributions have a certain normalizing constant, so we could just set this equal to the normalizing constant for this gamma distribution. Then we are very, very close to find, because this integral looks very much like the PDF of a beta distribution, except that where's the normalizing constant? And basically what we can do is use this to find the normalizing constant of a general beta.